Right. First up, we have Andreas Dilger from Intel. Andreas has been involved in the development of Lustre since before its inception. From early prototypes in 2000, before the founding of Cluster File Systems, through Cluster File Systems, Sun Microsystems, and Oracle over the next 10 years, Andreas was one of the lead Lustre developers. Andreas joined Wham Cloud in 2011 and continued to lead the overall design and development of Lustre. With Intel's acquisition of Wham Cloud in 2012, Andreas has moved into the position of Principal Lustre Architect. Andreas studied electrical engineering and computer science at the University of Calgary, where he earned his BSc degree. Andreas is going to be speaking with us today about Lustre 2.8 and beyond. Ladies and gentlemen, Andreas Dilger.
Thank you. Hi, good morning, everybody. So today I'm talking about Lustre 2.8 and the features that are being worked on there. Okay, so this is something else. So one of the things to start with is that we're working on a few new changes to the process of development. Chris has touched on those as well yesterday. And I think just as part of Lustre itself maturing, the development process itself is getting better. And we're working hard to make sure that the quality of the code in Lustre is robust and avoiding issues within really any patches that are landing. Currently we test for every patch. Okay, so this is I don't know what this is, but okay. We test Lustre pretty thoroughly for every patch that is pushed into the master branch, and the quality of any given Lustre release, any given point of time is pretty solid. So the features that we're talking about today sort of split into two camps. One is features that are pretty much ready for landing or intended to land within the 2.8 time frame, and others are features that are undergoing development currently, but are not necessarily ready to be landed for 2.8. And in some of the cases, I've listed versions beside them, and those are all target versions and not necessarily set in stone. But we're trying to complete features within the time frame of the feature landing window, and if they're not ready in time, they'll slip, but it's our goal to get them ready for those versions. So the first one is the last phase of the Lustre file system checker. The phase 4 is primarily concerned with improving the performance, and so during the earlier phases, obviously there was some attention being paid for performance in general. The majority of the implementation phase was targeted at functionality, and so the phase 4 collected a number of issues that we had identified during the earlier development phases as needing further attention, and so we've been running some benchmarks, and some of the improvements that have gone in to the phase 4 are improved scanning of objects in LDiskFS. One of the things that's also worth mentioning is that LFS check can also run on ZFS backed file systems. It doesn't do the very low level scanning itself in terms the same as it does on LDiskFS, but the higher levels of LFS check are verifying cross MDS and MDT MDS and OSS consistency, some of the Lustre extended attributes and things like that are being verified. As well, reducing locking overhead within the code is, improve the performance noticeably, and doing some optimistic locking. Like when LFS check runs currently, it runs without taking DLM locks, and so the assumption is that when it's running, the chances of finding inconsistencies are very small, and so you don't want this background scanning process to be locking and blocking your user processes. And so there's two cases where you can find an inconsistency. One is, if there really is an inconsistency, and then if you detect an inconsistency, you go back, you lock, you re-verify, you see, was this really an inconsistency on disk, or was this just a race condition, just at the millisecond that I was reading this object, somebody else was renaming it or deleting it or whatever. And so if that's the rare case, we don't want to be imposing overhead. And but the predictive locking means that if we've hit errors recently and they were persistent errors on disk, then we go into a mode where we are taking the locks, because the assumption is that we've hit a bunch of errors in a row, there must be something that needs to be fixed, and so we'll avoid the double checking until such a time that we stop hitting errors, and so that just improves the performance a bit. And then also improving the logging of LFS check related messages into the Lustre debug logs. So reducing in some cases the amount of errors that are logged for low level, developer level debugging, and making sure that whatever is logged under the LFS check, debug level is really useful for administrators to see what's going wrong with the file system. If there's common cases of, let's say you upgrade a file system from 1.8 to 2x, and you don't have FIDs on your file system, it will report that once, but it's not going to print 350 million or a billion error messages into the log saying, oh, you don't have a FID here either, right? So this is the final phase of the LFS check project, and for background, for people that don't know or haven't seen previous presentations, on most of the slides I've linked to previous presentations or the design documents and things like that, so people can get more information about these particular features. So D&E Phase 2 is focused on Stripe directories, and so this has been ongoing for a while. D&E, a long time coming, but I think a lot of people are happy that it's finally here. This is also the last phase of the distributed namespace project, and the goal of the Stripe directories work is to spread a single directory that might be created if you have a file per process workload. Every thread in your 100,000 core, million core system is creating one file in the same directory, right? And so you need high performance even within a single directory. And so with Phase 2 Stripe directories, you can spread the metadata workload across multiple directories, and that isolates, it scales up your create performance, unlink, in parallel in terms of distributed like DLM locking at the Lustre level, but also internally within the file system, you're reducing contention because you have multiple super blocks, you have multiple disk, IO queues and things like that. And so it provides pretty good scaling within one directory as well. And so this is, I should have mentioned here too, LFS check is funded by OpenSFS. D&E is also funded by OpenSFS and implemented by Intel. And So the last bit of DNE2 that remains to land for 2.8. So the stripe directories is in 2.6 and 2.7. It's a preview feature because there are certain things that you can't do in the remote directory case and in 2.4 and 2.5, and in the stripe directory case for 2.6 and 2.7, you can't do renames across MDTs. That's one of the limitations, and you can't do hard links. In some cases, like MV, like the user space command, it will handle the error return and do a copy for you, but it's not atomic semantics that comply with POSIX. So depending on what your workload is, who cares, because HPC workloads don't necessarily do lots of renames, but it's workload specific. The asynchronous commit provides a distributed recovery mechanism, and it's essentially write-ahead logging in the sense that each server that's involved in a distributed transaction holds a full copy of all the changes that are being made to the metadata server. And so if that change commits anywhere, then you have a full copy of all the changes, and in case of a crash, the metadata server that crashed comes up and asks all of its peers if it has logs that need to be replayed, and so you can always redo the changes that were committed elsewhere. Of course, if you crash before anything commits anywhere, no harm, no foul, right? You're still in a consistent state, and so this provides atomic transaction behavior. And it also, the asynchronous commit, as you can tell by the name, it avoids doing a synchronous commit on both sides of the operation, as happens today if you're doing in the 2.4 to 2.7, you have to do a sync on the master MDT and a sync on any remote MDTs, and so that makes remote or stripe directory creation more expensive than it needs to be. With the asynchronous commit, you don't have to sync. There are still some ordering issues where if you have, let's say, you're creating a series of stripe directories nested, there you have to make sure that you can recover that. So there still are ordering cases where you have to flush your commits, but they're definitely reduced. And as part of this, you can have the atomic updates allows you to do consistent renames, and you won't have a crash where you have the same name appearing in two places after a rename or something like that, or your link counts are wrong. And the other interesting thing with asynchronous commits is because it's a distributed transaction mechanism, you could potentially do something like write your metadata into two metadata targets at the same time for mirroring, right? Or you could at least, one of the gaps today is that if your MDS 0 goes down, your root, file system root, is inaccessible. So you could potentially, let's say, mirror the top part of the file system and still have accessibility to other parts of your file system and have performance scaling for the top of the tree. I mean, this is a future feature, but it's something enabled by this work. As well, there's ongoing performance improvements for single clients. In the old days of Lustre, we started with single processor machines, right? And 2 cores was, great. And now, you're getting into machines that have hundreds of cores. And so the performance and scalability of a single node is increasingly important. And so there have been improvements done in 2.6 and 2.7, but there's more on the way in terms of increasing multi-threading, NUMA, core awareness with memory, affinity, and things like that. There's client I/O code cleanups to make the code more accessible and understandable to users, and just optimize the internal implementation. And larger RPC sizes, have shown improvements in certain workloads. And so, you know, in addition to single client performance, the single threaded performance is you know, important in some workloads. So there's ongoing work there. As well, in addition to the I/O performance, there's improvements in the metadata performance, and so the metadata RPC scaling, you know, originally was designed, like I said, for, you know, single core machines. So you had one, you know, thread that could do creates and unlinks. So this is again becoming a performance bottleneck on one system, and so Bull and Intel are working together to improve the RPC scaling. I mean, it's not just a matter of, you know, flipping the switch and saying, now you can do lots more RPCs. There's recovery implications to get multiple transaction updates happening consistently on the server in case of server failure. And so the graphs below, they show create, this is a prototype, but it shows create and unlink performance. The bottom line is the current performance. I think this was like 2.350 or something like that, or 2.450. The bottom line is the current performance with the RPC serialization, and some early testing just to disable the serialization shows that there's, you know, a lot of headroom in terms of what a single client can do with multiple threads. And so work is ongoing to implement the multi-RPC support, and that's intended to be completed for 2.8 as well. There's support for newer newer Intel InfiniBand adapters coming in as well. The biggest difference is, even though they work with OFED, is that the tuning is essentially the opposite of what's the best for Mellanox. And so there's a bit of infrastructure work being done to allow you to optimize, you know, at runtime to detect, you know, what kind of underlying network interfaces you have, and pick the right tuning parameters. You know, the current Lustre stack, you know, had been optimized for Mellanox for a number of years, and it picks the default that are best for Mellanox. But obviously some people we work with would like it to work better out of the box with Intel as well. And so continuing on with dynamic LNet config, that was landed initially in 2.7. It's going to work on allowing per network interface tunables, which, you know, in WAN or other environments where you have, let's say, two InfiniBand adapters in the same node, but they need different tunables on either side. The DLC2 will you know, allow you to set different tunables. And so that's probably not going to make it into 2.8. That's into the 2.9 range, or the target at least. So there's ongoing work to improve ZFS. And as you saw the presentations yesterday, you know, we were working with San Diego to improve some of the performance that they saw. And you know, Brian and the ZFS team has been working on you know, increasing the block size for ZFS. You know, we did some optimization at the Lustre level to improve the read performance. And another thing that has been missing from the Lustre use of ZFS is the ZFS intent log, which is optimization for synchronous writes. And that allows you to use essentially Flash as a log for synchronous updates. And while Lustre itself usually uses asynchronous, you know, updates on the servers, there are workloads, you know, if you have multiple files, multiple clients accessing the same file, where you get a lot of commits to disk. And so that can help there dramatically. Bigger changes in the future is related to parity declustering and distributed hot spares at the ZFS level. And so that's a bit farther out. It's about 2.10, so targeted about a year away, year and a half. And but that's to ensure that the rebuild time on increasingly large ZFS pools stays within acceptable range. Protocol documentation is not really tied to a specific Lustre release, but it's describing what goes over the wire, and is intended to help newer developers understand what's happening with Lustre, and even existing developers to understand what's really going on, rather than what their mental model might have grown into. And so this is a process that's just going through the different types of file system operations and what kind of network traffic do they generate on the wire, and then going through and describing all the structures and what kind of state changes they make. So it should be a very useful resource. This is just ongoing, and there's a contract, there's a Git repository that's starting to get some content into it. So last year, Intel and OpenSFS worked on a project to design Data-on-MDT, and the target here is improving small file performance. And essentially, one of the issues is, Lustre was originally designed for large streaming I/O workloads, and so overhead of a single file open was not a primary design goal. But as Lustre works into other spaces, the small file, and even in HPC there are small file workloads, and so avoiding some of the RPCs, avoiding disk seeks on the OSTs, especially if you have other high throughput workloads, you're penalizing both workloads by having lots of small IOs, and avoiding MDT storage is RAID 10. It's optimized for IOPS. OSTs are RAID 6, and so if you are doing small file IO to OSTs, typically you have a read modify write penalty, and those are all things you can avoid by storing data on the MDT. And so what it consists of, a small file is determined by the administrator and or the user. The administrator puts on an upper size limit, typically let's say a megabyte, and the user you set the striping on the file when they create it, which will maybe reduce the size of what is considered a small file. And this feature, storing the data on the MDT, complements nicely with stripe directories. You can create a stripe directory over all your MDTs, and then the files, the small files, will be distributed over all your MDTs as well. And so you can horizontally scale your small file performance. And right off the bat, there's expected to be a 2 to 3 times performance improvement just by removing RPCs to the OSTs for locking and then fetching attributes and things like that, or fetching the data. With further work on the Data-on-MDT, you could potentially extend the stata head feature to be also fetching small file directory data, in a single RPC. So you get the attributes, you open the file, you read the data, without having multiple network round trips. So the progressive file prototype is between a project with Intel and Oak Ridge. John Hammond will be talking about this more soon. It's essentially trying to simplify the user's world of having to select striping in advance, right? So this way they can specify a progressive file striping. If their files don't grow very large, they only get one stripe and the overhead of one stripe. If the files grow huge, they can stripe over all their OSTs and get all the bandwidth. Won't spend too much time on that. There's a few other miscellaneous features that are being worked on, sort of ongoing code cleanups. Oak Ridge, Cray are helping out there a great amount, and that's really making Lustre, more understandable. It's helping with the upstream integration, removing, tens of thousands of lines of dead code, either because of, obsolete compatibility with old kernels or what have you. And project quotas is something DDN is working on, and they're currently, fighting the good fight with the upstream Linux developers to get project quotas into ext4. And then once that's done, when we've finalized all of the disk formats, we'll have that in Lustre as well. And as you saw yesterday, there was work ongoing with authentication and encryption of clients and users, and that's interesting to lots of people. And I believe that that's it. Tells you we don't know when these features will be in, but those are our best guesses. I think I have 1 minute for questions.
Progressive file striping, do you have any guess on when that might come into play?
Currently it's just a proof of concept, and so we don't have a firm target for that yet, which is why there's no number listed. But the prototype is targeted to be done this summer. So beyond that, the rough estimate might be about a year after, but there's no hard plan for when that's going to be developed.
So I've got a question.
Yeah.
So OpenSFS is currently paying for this protocols documentation. You
Yep.
said that would be ongoing. Do you anticipate, are you anticipating that OpenSFS will continue funding this, or is this something that Intel plans to keep up to date, or are you going to rely on the community?
I think a combination of those things, right? Obviously there's, there's a large amount of upfront work to develop the documentation initially, and so OpenSFS is funding us to do that currently. Because Intel does a large amount of the development and changes to the protocol, that would be something that's folded into the newer development projects, right? And obviously, community assistance would be welcome, but I don't expect, we don't get any, hardly any contribution to user manual, which is something that any Lustre user could update. And so for them to update the protocol manual, I don't see that as happening very much.
Okay, thanks.
Multiple mount protection on ZFS? Multiple mount protection on ZFS, can you give a time frame on that, and what are the major hurdles?
So there's a design that we worked on back at Sun, and I don't think that there's, it's mostly an implementation task. It's not that we have to figure out how to do it at this point. That's something that it's still, a year away before we could get people working on that, I think. But it's something that is important to all ZFS users, and that's something that we're supporting. So there will be resources allocated to it. It's just that we have all these other projects that are still wrapping up, and we have to see who can work on those. Okay, I think I'm out of time, but no questions. All right, thank you.
Thanks, Andreas.